Hey everyone, welcome back to the channel. In this video, I'm excited to share with you the latest update on my Laser Project 2.0. I'll be taking you through the full documentation, behind-the-scenes progress, and some of the key improvements I've made along the way. Whether you're here for the tech, the process, or just curious how it all comes together, you're in the right place. Let's dive in. In this part of the video, I'm going through the components from my original Laser project, the first version before Laser Project 2.0. As you can see, I've disassembled most of the old setup to sort out which parts are still in good condition and potentially reusable. This step is important, not just for saving costs, but also for understanding how far the project has come and what improvements are needed moving forward. Now, just to clarify, none of these parts are being thrown away. I make it a habit to keep any component that's still functional or might be repurposed in future builds. You never know when a driver, a power supply, or even mounting hardware might come in handy for testing or for prototyping other designs. Keeping organized and preserving good parts is part of my workflow to stay efficient and sustainable with each project. That said, not everything survived perfectly. Most components are still working, but the Galvo scanner, unfortunately, has started showing signs of wear or internal malfunction. It's not reliable enough for precision tasks anymore, which is why I'm currently assessing its condition and whether it can be salvaged or replaced. For the time being, I'm still testing some of these parts to see if they can contribute to Laser Project 2.0, but anything that doesn't make the cut will be safely stored for future experiments. Now in this segment, I'm starting the disassembly process. I'm carefully removing each component one by one, making sure not to damage anything in the process. Precision is key here, not just for safety, but to make sure the parts stay in usable condition for later testing. Every piece I remove is inspected and set aside properly. Even if I'm not using these parts right away in Laser Project 2.0, they could still be useful for some rough testing or quick setups in the future. Having a collection of known working components makes experimenting a lot easier when new ideas come up. It's also a good opportunity to get a closer look at how everything was originally connected. That helps me take note of what worked, what didn't, and what can be improved this time around. So, it's not just about disassembly, it's also part of the learning and rebuilding process. Most of the components I'm removing here are quite basic, things like mounts, wires, brackets, and small modules, but that doesn't make them useless. In fact, these kinds of parts are often the most helpful during early-stage prototyping. When you're experimenting or trying out rough setups, having a collection of spare parts like these saves a lot of time and effort. That's why I make sure to hold on to them. They might not look like much now, but they could play an important role in testing future ideas. Along with salvaging electronic components, I've also restored and modified some parts of the original housing or laser enclosure. Instead of building everything from scratch, I decided to reuse sections of the frame and enclosure panels that were still in good condition. With a few adjustments and modifications, they're now better suited to fit the updated design of Laser Project 2.0. It's a great way to save time and material while still maintaining a strong and reliable structure. In this next step, I decided to do a rough installation of my new 40 kpps Galvo along with its driver. To speed up the process and get some early feedback, I'm using some of the salvaged components from the old laser system, just to test compatibility and layout options inside the laser unit. This isn't the final installation yet, think of it more as a trial run. I'm mainly checking how well the new Galvo setup fits within the existing enclosure and whether there are any issues with space, alignment, or wiring. It's also a good chance to see how the old components respond when paired with the new system, and if there's any unexpected behavior during the initial power-up and signal testing. Doing this kind of early setup helps identify potential problems before moving on to a full build. It also gives me a clearer idea of how the final arrangement should be for optimal performance and accessibility. The idea behind this setup is to get a practical sense of how everything might work together in the final build. Instead of relying purely on planning or design sketches, physically placing the components allows me to observe airflow, cable routing, mounting points, and possible interference between parts. It's a hands-on way to fine-tune the layout before committing to a permanent installation, and it often reveals small but important details that might be missed on paper. Now we're moving on to the initial test run of the new 40 kpps Galvo system. For this test, I'm using some of the old laser components along with my DIY prototype RGB laser source as a temporary decoy. It's not the final laser module, but it serves the purpose for this stage, allowing me to safely test the Galvo's movement and signal response without risking high-end hardware. This testing procedure is a critical step. It helps verify the basic functionality of the Galvo system, checking if the driver is receiving signals properly, if the mirrors are tracking smoothly, and if the overall setup can handle input from the controller. Even though this is a rough setup, it gives valuable insight into potential alignment issues, signal noise, or power inconsistencies that need to be addressed before final assembly. Fundamentally, this stage is about building confidence in the system. It's where theory meets reality, and where I can catch any hardware or wiring problems early on. Testing with a decoy laser also ensures that I'm not risking sensitive or expensive components while still getting real-world data on performance and stability. In this stage, I'm now testing the setup using an ILDA input, connecting it to my Pangolin FB3 controller and running QuickShow to send some basic animations to the laser system. This test helps me evaluate the Galvo's response in a more realistic scenario, checking not just movement, but also how the laser handles color transitions and complex signal patterns from actual software control. One of the key goals here was to determine whether the old laser components operate on an analog signal or TTL. As I ran different color configurations through QuickShow, I started noticing some inconsistencies. Certain colors weren't displaying correctly, or were flickering in unexpected ways. After a bit of signal tracing and troubleshooting, I confirmed that the old system only supports TTL input, which explains the limited color handling and abrupt changes. Because of that limitation, I decided it was best to remove the old laser modules from the build. While they were useful for early testing, they just don't meet the flexibility and precision I need for Laser Project 2.0. I'm keeping only the components that still align with the project goals, ones that offer stable performance and can integrate properly with a fully analog RGB system in the final design. After identifying the limitations of the old laser system, I decided to move forward by building a direct ILDA input connection myself. Using the standard ILDA pinout configuration, I started wiring each signal line manually, making sure to follow the correct mapping for X and Y axis control, as well as the RGB analog signal inputs. The goal here is to have a clean and reliable ILDA interface that connects straight from the Pangolin FB3 to the Galvo driver and the new analog-compatible laser module. By bypassing the older wiring and routing everything directly, I can ensure a more accurate signal path with less interference or signal loss. Each pin from the ILDA connector was carefully wired to its designated input, the Galvo driver for X and Y, and the analog inputs on the laser drivers for red, green, and blue channels. This setup not only improves signal quality, but also gives me full control over the system's performance, especially when working with color gradients, fades, and more complex show programming. Before connecting my final ILDA input and output port, I'm using this prototype ILDA wiring setup to make sure everything is working correctly. It's a temporary configuration where each wire is accessible and easy to trace, which makes troubleshooting and adjustments much simpler during these early testing stages. This prototype setup allows me to verify signal flow from the ILDA input to both the Galvo drivers and the analog laser drivers, ensuring the wiring is correct and each channel is responding as expected. It's especially useful for spotting any mistakes in pin mapping or signal inconsistencies before locking everything into a more permanent configuration. The idea behind this approach is all about reducing risk. By confirming that everything runs smoothly with the prototype, I can confidently move forward with my latest, fully soldered ILDA input and output port. That final version will be much cleaner and reliable, but having this flexible test stage helps avoid costly errors and gives me more control over the setup process. That said, the test still shows some noticeable inconsistencies, mostly in how the color channels respond and how smoothly the Galvo tracks certain patterns. These issues are likely caused by slight mismatches in signal grounding or voltage levels across the prototype wiring. So, a few more tweaks are needed to clean up the signal distribution and ensure proper synchronization between the controller, Galvo, and laser drivers. At this point, the ILDA wiring and signal configurations have been fixed and everything is now functioning as expected. The Galvo is responding properly, and the signal flow between the controller and the laser drivers is stable. However, you might notice that the color output still isn't accurate. That's because I'm currently using a prototype RGB laser source, and the green diode in this unit is noticeably weak. As a result, what should appear as white in the line patterns is showing up more purple due to the imbalance between the red, green, and blue channels. On top of that, as you can probably see, the internal wiring is still a bit messy. While it's fine for testing, it needs a proper cleanup to make the setup more organized and reliable. Tidying up the cable routing will help improve airflow, reduce signal interference, and make future upgrades or troubleshooting much easier. Here, I'm doing a rough beam test of the entire unit to show that everything is working as expected with the Galvo setup. The mirrors are tracking properly, the ILDA signal is being received correctly, and the test patterns are displaying smoothly, even with the temporary laser source in place. This kind of beam test is important because it gives a visual confirmation that all core components, like the Galvo, driver, and signal routing, are functioning in sync. It also helps me observe how the system performs under live output conditions, which is something that wiring diagrams and software simulations alone can't fully reveal. Even though it's still a basic and temporary setup, this test confirms that the foundation of Laser Project 2.0 is solid and ready for refinement in the next stages. In this part of the project, I've modified the original laser unit's aperture to make it more refined and focused on safety. The old opening wasn't designed for higher powered modules, so I've redesigned the structure to better manage beam output and limit stray reflections, which is especially important for safety. This adjustment is in preparation for the final installation of a 6-watt RGB laser module, which will serve as the main laser source for Laser Project 2.0. With that level of power, proper aperture control and enclosure design become critical, not just for performance, but to ensure everything remains safe during operation and testing. The new design also helps align the beam path more precisely with the Galvo mirrors, which is essential for clean and accurate output once the final laser module is in place. I've replaced the old power input with a PowerCon connector. It's a safer and more reliable option, lockable, rated for higher current, and perfect for handling the power demands of this upgraded laser system. This change improves both safety and overall durability for the project. In this part of the build, I took the time to repaint and modify the laser unit's enclosure housing. The goal here was not just aesthetics, but also to prepare the structure for a more reliable installation of custom brackets and mounting points. These changes are especially important as I move forward with integrating higher-powered components like the 6-watt RGB laser module. By reinforcing and adjusting the enclosure, I can ensure that all internal parts, such as the Galvos, drivers, and power supply, are mounted securely with minimal movement. This greatly reduces the chance of vibrations or misalignments that could affect performance and beam accuracy. Additionally, these modifications contribute to overall safety. A more stable internal layout means less risk of components coming loose or wires shifting during operation, which is critical when working with high-power lasers. It also improves airflow and makes future maintenance or upgrades much easier. Right on schedule, the 6-watt RGB laser module from Laser has just arrived, and this marks a major milestone for Laser Project 2.0. I've been waiting for this unit to move forward with the final stage of the build, and its arrival couldn't have come at a better time. This module combines high output power with compact design, making it ideal for both hobby and semi-professional laser systems. It features a full-spectrum RGB output with analog modulation, allowing for smooth color blending and more dynamic control when used with ILDA-based systems. Each diode, red, green, and blue, is independently driven, ensuring balanced brightness and high stability across various beam patterns. Laser is known for solid build quality and thermal efficiency, and this model includes an integrated cooling system to maintain performance during extended operation. The beam specs are also quite impressive, offering tight divergence and consistent output, key for producing crisp, sharp projections through the Galvo system. Unboxing this unit is exciting because it means I can finally begin integrating the main laser source and see how it performs in a real-world setup. Now it's time to put the 6-watt RGB laser module to the test. I've done a rough alignment of the laser to the Galvo system and connected it using my prototype ILDA input to evaluate overall stability and functionality. This stage is crucial. It allows me to check how well the new laser source performs in real conditions, including how it responds to analog modulation signals, how clean the beam output is across all colors, and how accurately the Galvos can under load. I'm paying close attention to thermal behavior, color consistency, and any potential signal noise coming from the temporary wiring setup. Even though the alignment isn't final yet, this rough configuration is enough to determine if the laser and Galvo are communicating correctly through the ILDA input. It also helps me spot any early issues before moving on to more precise optical alignment and permanent wiring. So far, everything is running smoothly, and this test confirms that the new laser module is a solid match for the system. In this stage, I've now permanently installed the 6-watt RGB laser module into the laser unit. With the power and signal systems already tested, the focus now shifts to precision optical alignment. To achieve this, I reused the existing dichroic mirror mount from the original setup, this time not for color separation, but to securely hold a high-quality front surface mirror. Front surface mirrors are essential in laser systems where precision is critical. Unlike standard mirrors, which reflect through a layer of glass, front surface mirrors reflect directly off the coated surface, eliminating ghosting and beam distortion. This is crucial for maintaining a clean, undistorted beam path as it reflects toward the Galvo system. Using the adjustable dichroic mount gives me precise control over the angle and positioning of the mirror, allowing fine-tuning of the beam trajectory into the Galvo mirrors. This ensures that the laser enters the Galvo optics at the exact alignment point needed for accurate scanning across both axes. By combining the power of the new RGB module with this refined optical path, the system is now much closer to professional-grade precision, and it sets the foundation for high-quality beam effects and reliable performance going forward. With the 6-watt RGB laser module fully installed and aligned, I'm now performing the first enclosed housing test. This stage is important because it simulates a more realistic operating environment, where the laser runs inside its sealed enclosure, just like it would in an actual show or final installation. Running the system inside the housing helps evaluate thermal behavior, internal airflow, and electromagnetic stability under load. I'm also making sure there's no light leakage or reflection issues that could pose safety risks or interfere with the beam path. For this test, I'm using Pangolin QuickShow to send laser graphics and animation effects via ILDA. This allows me to verify how well the Galvo system tracks complex patterns and transitions in real time. I'm closely monitoring color blending, corner accuracy, and scan speed to ensure the visuals are crisp and stable. This enclosed environment test is also a good opportunity to fine-tune internal layout decisions, like cable routing, ventilation, and component spacing, while confirming that the entire system is performance-ready. In this segment, I'm testing Laser Project 2.0 in a daisy-chain setup with my first DIY laser unit. Both units are equipped with 6-watt RGB laser modules, and I'm using a single Pangolin FB3 controller to drive them simultaneously. The concept behind this test is to see how well two laser systems can operate in sync from one ILDA output source. By daisy-chaining the ILDA output from the FB3, the laser signals are passed from the controller to the first unit, then forwarded to the second. This allows both units to display coordinated animations and effects, expanding the overall visual impact without needing multiple controllers. This setup is especially useful for multi-projector shows or larger-scale installations where syncing several laser units is necessary. During the test, I'm focusing on signal integrity, timing accuracy, and whether the power and modulation signals remain consistent across both devices. Running this simultaneous output test helps confirm that the new Laser Project 2.0 integrates smoothly with existing hardware and can be part of more complex laser setups in the future. To wrap up this phase of Laser Project 2.0, I've installed a custom bracket onto the laser unit enclosure. This bracket serves a critical role in providing additional mechanical support and stability, especially during transport and live shows where the equipment might be subject to vibrations or accidental bumps. The custom bracket is designed to securely hold the entire enclosure in place when mounted on a stand or rig, preventing any unwanted movement that could affect the precision alignment of the Galvo system and laser optics. Stability is key in laser projection, as even minor shifts can cause distortion in the projected patterns or reduce overall image quality. Beyond support, this bracket also enhances safety by ensuring that the laser unit is firmly anchored, reducing the risk of the enclosure falling or shifting unexpectedly during operation. It's an essential upgrade for any project intended for public demonstrations or performances, where both the equipment's performance and the safety of the audience and operators are top priorities. And that wraps up the journey of Laser Project 2.0. From careful disassembly and testing to installing a powerful new 6-watt RGB laser module and refining every detail along the way, this project has been an incredible learning experience and a true labor of passion. I hope this video inspires you to explore your own laser projects and keep pushing the boundaries of creativity and technology. Remember, every step, no matter how small, brings you closer to turning your ideas into reality. If you enjoyed this deep dive into the world of laser systems, please don't forget to like, share, and subscribe to the channel. Your support means a lot and helps me bring more exciting projects like this to life. Thanks so much for taking the time to watch, and I can't wait to share more with you soon.